This is a lesson on one of the consequences of Einstein's theory of special relativity. I'm going to start with time dilation. It's absolutely amazing, the implications of this idea. And it's really just using simple maths, simple high school, junior maths, no complex calculus, nothing like that. It's very simple maths, as we'll see, will show that there's really more to this theory. So previously we've seen that there are consequences for having equivalent inertial frames of reference from Einstein's two postulates of special relativity. The first one is that the laws of physics remain unchanged, or in other words, they're invariant. Remain unchanged in inertial frames of reference. In other words, reference frames involving someone or an object being stationary, not moving in other words, or an object moving at constant velocity, okay, where Newton's first law of inertia applies. And the second law, second postulate, I should say, is the invariance of C. Okay, in other words, the speed of light is the same for all observers, regardless of your motion. Okay, these were proposed by Einstein in 1905. Okay, and Einstein's postulates also imply that there's no such thing as an absolute reference frame. Okay, one in which we can compare our measurements and results to. Okay, in other words, all motion is relative. That's Einstein's big idea. So the time that you measure is different to the time I measure. And similarly with lengths and distances and energy and mass as well, for that matter, as we'll see. You can only say that something is moving with respect to something else, okay, relative to something else, and not that there's something which is actually at rest, as Newton believed, this master clock in the universe, sitting out there in the universe. In the HSC, we'll be exploring 4 of the main consequences of Einstein's special relativity. Here they are. Okay, the first one in this particular order is time dilation. Second one is length contraction. Third one is relativistic momentum. And the fourth one is Einstein's energy mass equivalence, okay, through E equals mc squared, his famous equation. So let's start with time dilation. Now, moving close to the speed of light, space and time become warped, and the effects become noticeable at these very high speeds, okay, as in contrast to everyday experience, which we don't notice. And through his brilliant imagination and intuition, Einstein developed thought experiments, okay? I want you to get used to the word thought experiment for the HSC. Thought experiment is basically a hypothetical experiment, okay, an imaginative experiment, okay, designed to extend and explore the implications of a theory, okay, that would be otherwise impossible to perform with current technology and experiments, okay, to then quantitatively derive relationships between things like space and time, okay, as measured by observers in different frames of reference. So that was Einstein's brilliant insight, to use thought experiments, I should say. So let's look at time dilation. It's a very simple concept to grasp using everyday objects, familiar objects. Let's suppose we have a train carriage moving along a track. Suppose there's an observer on in the carriage, and suppose there's another observer watching on the platform. And suppose the train carriage is moving at constant velocity v to the right, and let's suppose that the observer on the train makes a clock, okay, using a pulse of light going from the top of the carriage and back, okay? So a pulse of light somehow is made of pulse of light that can travel up and down. Let's suppose that these two things are mirrors here. He somehow managed to make a clock using a pulse of light going up and down, bouncing back and forth between the mirrors. And the observer on the train would see the pulse going up and down, okay? There's nothing special, nothing mysterious here. That's what's expected, right? Similarly, if you take a ball, okay, you're on a train, the train's moving at constant velocity, You take a ball, you bounce it, it bounces up and down. Okay, there's no mysteries there. And Einstein, through Einstein's postulates, the observer in the train is actually at rest with respect to the clock, right? He's not moving with respect to the clock, in other words. So the observer and the clock are basically moving together, okay, at constant velocity with the train. That's an inertial frame of reference. Suppose the time it takes for the pulse to make the round trip is denoted by t sub naught. Okay, the time it takes to go up and then back down. And the height of the carriage is h. Height of carriage is h. Okay, h for height. So therefore, the observer, so let's call the observer in the carriage A, observer on the platform B. Let's suppose that A will find that the height, okay, is given by c t sub naught over 2. And I'll tell you why. Remember, velocity is distance divided by time. For the speed of light, let's replace v with c, okay, because light moves at the speed of light c, equals h. We're using the distance h in this case, height of the carriage. And t is the time, t sub naught, so therefore h is equal to c t sub naught. That's where I got this expression from. Now divided by 2 because we're dividing the round trip by 2. Okay, we just want the distance that the light pulse travels from the bottom to the top, let's say, or from the top to the bottom. That's why we're dividing by 2. Now the observer on the platform B will see something different. He'll actually see the beam move through a longer distance during t sub naught, okay, the round trip. But both must agree on the speed of light. Okay, if both observers have to agree that the speed of light's the same, then the observer on the outside of the train would observe the time of the light pulse to be different, as we'll see. Okay, and for this to occur, the length of the path taken by the light to reach the top of the carriage will have to be given by c t over 2. Okay, just as the case is for the observer inside the carriage. So let's draw some diagrams here to see what's happening. Okay, according to the observer on the platform B, let's take a look at what they would see. So suppose 3 snapshots of the train moving at constant velocity to the right v in time, and the guy on the platform is just looking at this, A and then this B. So I've got 3 snapshots in time. According to the observer B on the platform, they would see the light beam doing this as the train is moving. The light beam would actually zigzag up, down. So in other words, for each line on the zigzag, the observer on the platform would see the length traveled was ct over 2. Okay, so ct over 2 here and ct over 2 here. All right. So that's what this guy would see. He would see ct over 2. Okay, the length of the path taken by the light to reach the top of the carriage. So let's puff up. Let's represent this. Repicture this as depict this as a triangle. Okay, so for the observer on the train, he would see the light pulse taking a straight line vertically, up, down. Observer on the platform B would see this. Okay, ct over 2, ct over 2. Okay, so it would travel at a much longer distance. Okay, ct naught over 2, right? This is a right angle triangle here. Okay, and these here would be vt over 2, vt over 2. Okay, because the train is moving at velocity v to the right, up here. So therefore you get vt over 2, you get half of that. I should say the vt came from, so remember v equals d over t, d is v over t. D is vt, I should say. So the distance travelled here, total distance is vt, but because the train is moving and the observer is watching on the platform, it's vt over 2. Okay, for these smaller sides of the right angle triangles. Let's use Pythagoras. So you don't need to derive this in HSC, it's just nice to know where it comes from. I'm just showing you using simple maths you can derive time dilation formula. Using Pythagoras, we can derive the following expression. So ct over 2 squared, let's take one of these right angle triangles, let's take this one here. on the right. So ct over 2 squared is equal to ct sub naught over 2 squared, okay, this length here, plus vt over 2 squared. Okay, so c squared is equal to a squared plus b squared. Okay, squaring all of this and cancelling out with the 2 squareds, so we get c squared, 2 squared, sorry, c squared t squared is equal to c squared t sub naught squared plus v squared t squared. Okay, we've skipped a step and I've basically divided everything by 1 over 4. Now let's find an expression that relates t and t sub naught. We can do this through the following. We can divide through by c squared. So we're left with t squared is equal to t sub naught squared plus v squared t squared over c squared. Let's reformulate this in terms of t sub naught squared. Okay, taking this guy over, t squared minus v squared t squared over c squared. And then factoring out the t squared, so t squared, we get 1 minus v squared over c squared. And then taking the square root of both sides, so we're left with t sub naught is equal to t square root of 1 minus v squared over c squared. And then therefore we can write that t is equal to t sub naught over square root of 1 minus v squared over c squared. And this is the time dilation formula. Now in everyday experience, the velocity of the train, in this case, v, is always going to be less than c, much smaller than c. And hence the denominator, which is this thing here, square root of 1 minus v squared over c squared, is always going to be less than 1. Okay, and it's going to be very small, in other words. So roughly, t will be equal to t sub naught. In other words, the time measured by the person in the carriage, okay, person B, will be the same as the time measured as the person on the platform A. Okay, so if one second passes for an observer on the platform, okay, the observer A, then you roughly get you get less than 1 second for the observer on the train. Okay, if the velocity is comparable to that to the speed of light. Okay, if the velocity of the train approaches the speed of light, the person on the platform, sorry, I should say the person in the carriage will find that time passes slower time for B. Okay, in other words, t sub naught will be less than t. Okay, this is an important statement. So this formula tells you that moving clocks run slow. Okay, the faster you move, the slower time runs, and this effect becomes very noticeable at very high speeds close to the speed of light. Okay, this is called time dilation, the infamous time dilation formula. Just using simple math, simple algebra, you can find some pretty impressive implications for reality as you move close to the speed of light. That's called time dilation. And time dilation, amazingly, actually works both ways, okay? And the two different situations are symmetric. In other words, the person who's on the train, person B, can claim themselves to be stationary, and the rest of the earth is moving with respect to them. So in other words, B can claim that A is moving and that they're stationary, and vice versa. Now, there was no experimental evidence at the time of time dilation in 1905, and so it took quite a while for a large amount of experimental evidence to be collected. Let's do a typical example, typical classic textbook example of muons, okay? So muons, these are subatomic particles. These are like the heavier versions of an electron. And muons are typically produced in cosmic ray collisions, okay? About 1.5 kilometers above Earth's surface. So 1.5 k's above Earth. Okay, and they travel at a velocity of around 0.99, okay, about 99% the speed of light, okay, due to the high energy collisions. So cosmic rays from space coming in, strike the atmosphere, and there's this really energetic, really violent collision. So that's why they move at such high speeds. Now on Earth, experiments have shown that they decay into an electron. So a muon is given by the symbol mu, Greek symbol mu, the minus sign, it's negatively charged, just like an electron. Decays into an electron, E minus, negative charge, and two what are called neutrinos, two electron neutrinos. I'll talk more about this in the next module. Okay, but in other words, you don't need to know this for the HSC syllabus. You just need to understand what's happening with muons. They come in the atmosphere. They're formed in cosmic ray collisions. They're very short-lived, okay, because they're quite heavy, and so they decay into three other particles, an electron and two electron neutrinos. Okay, with a half-life, in other words, of a lifetime of 2.2 microseconds, so 2.2 times 10 to the minus 6 seconds. They're very short-lived and very unstable subatomic particles. Let's suppose the half-life of a muon produced in the atmosphere. Let's suppose we need to work out the half-life, I should say. Half-life of a muon produced in atmosphere. And we need to work out how far a muon travels through the atmosphere as measured in the muon's frame of reference. Okay, a bit wordy, but let's break this down. So we need to work out the half-life of a muon produced in the atmosphere and how far it would travel through the atmosphere in the frame of reference of the muon itself. So pretending to be a muon heading towards the atmosphere. What's its lifetime? What's its half-life? Now the muon's frame of reference, the muon is at rest. Okay, it's not moving, and everything else is moving with respect to it. The Earth is moving with respect to it. So its half-life would therefore be, according to the question, that's what we're given, 2.2 microseconds. Now the distance traveled by the muon is quite simple to work out. D equals V times T. Distance is velocity times time. Its velocity is 99% the speed of light, so it's 99.99 times the speed of light, 3 times 10 to the 8, times its lifetime, 2.2 times 10 to the minus 6, and you get 653 meters in the muon's frame of reference. And now suppose we want to work out the half-life as measured by an observer. Half-life measured by observer at rest, okay, on Earth's surface. Suppose you have a scientist on Earth's surface watching these muons, and he wants to know what the half-life is. Okay, looking at the muons. So we need to use the time dilation equation for this. So T is equal to T sub naught over square root 1 minus V squared over C squared. And as I said before, you don't need to memorize this. It's given in the formula sheet in HSC. So T sub naught, in other words, this is the time as measured by, I should say, moving object. And T is the time measured by the stationary object. Now, time is measured by the moving object, the muon in this case. It's 2.2 microseconds. It's 10 to the minus 6 square root 1 minus V squared. So it's moving at 0.99 times 3 times 10 to the 10. 3 times 10 to the 8, sorry. Actually, best to keep it like this. 0.99 C squared over C squared. That'll give us the C squareds cancel and you get 15.6 microseconds. So if you work it out and you convert it to microseconds, you get 15.6 microseconds. And also the distance. Suppose we need to work out the distance traveled by the muon as measured by an observer on the Earth, the scientist that's looking on. As before, D equals V times T. V is 0.99, once again, times the speed of light, times the time, which in this case is 15.6 microseconds, times 10 to the minus 6, 4,633 meters. So the muon, according to an observer on Earth, will travel a distance of just over 4.5 kilometers, as opposed to the muon in its own reference frame, it will travel 653 meters. So the distances, as you can see, they're different. Okay, the muon measures distance differently to the observer. And similarly with the time, half-life 2.2 microseconds in the muon's reference frame and 15.6 microseconds in the observer's reference frame. So in other words, moving objects experience time less, as indicated by this 2.2 microseconds. And that's time dilation.